Hi guys, am I audible to all of you? Hi guys, am I audible to all of Yeah, I think I'm audible. Okay, and you're getting my video as well, right? Fine guys. So in this video we are going to see the introduction to semiconductors. Okay. So introduction to semiconductors means all of you know that it is the first unit of the UGC NET electronic science. Okay, so in this video I'm going to give you one brief idea regarding the unit 1. Okay, so what are the topics it will be having, and just little bit introduction to the each and every topic. Okay, and how we have to deal with this first unit. Okay, so which type of questions we may expect. So all these things we are going to discuss in this video guys. So before going into all these things, here one announcement is that the complete course for the UGC NET electronic science as well as the paper 1, that is general paper 1. So both these two, the complete course already started guys. While coming to the paper 1, so paper 1 is started from November 9th onwards, and electronic science started from November 10th onwards. So the interested candidates may take the subscription plan to get the complete course of both these two guys. Okay, so if you take the subscription plan now, you may watch the previously done as a recorded videos, and whatever the upcoming classes are there, you may participate online. So here the live classes are going to interact with both much. So whatever the queries or the doubts you are having, you may ask your queries guys. Okay, so a lot of flexibility will be there, and for each and every 3 sessions, one doubt clarifying session also will be there. So it will be very much helpful to you to clear your doubts. Okay, and the classes will go on the complete interaction basis. Okay, so here the different subscription plans are there. So you may take the 1 month, 3 months, 6 months, 12 months or 24 months. So it depends upon when you are planning to write the exam. So you may take any one of the subscription plan. But soon these prices are going to hike. Okay, these prices are going to increase guys. So before increasing these subscription plans, so if you are planning to write the exam and if you are interested, then you may take the subscription plan right now without waiting. Okay, so if you wait, the soon the prices will hike. Okay, and if you are planning my Unacademy profile link as well as a subscription link, both these two are available in the description box of this video. So you may check down that one. And if you are planning to take the subscription plan, then use my referral code, that is Aswini K. Then you are going to get the 10% discount on any one of the subscription plan. Okay, so it is a thing that what I want to tell. So now we will go into the present topic, that is the introduction to semiconductors. So coming to the introduction to semiconductors. So in this one we are having the topics like we have to know about the first one, semiconductors. So in the semiconductors, what are the topics we have to, subtopics we have to learn that. First one, regarding the bonds, covalent bonds and bands, nothing but energy bands. Okay, and how the energy bands vary with respect to the temperature. And you have to know the energy bands for the three materials. One is for the metal, and second one is for the insulator, and third one for the semiconductor. So you have to know the energy bands of this one. So just I will give you some little bit introduction regarding this one. So coming to the semiconductor is nothing but the conductivity or the resistivity or all the properties which lies between the metal and the insulator. That's why it is called as a semiconductor. We can also call as a semi-insulator, but it will give the negative sense. So that's why we are calling as a semiconductors. Fine. And coming to the bonds, so whatever the bonds those are existing in the semiconductors are the covalent bonds, which are very sensitive to the temperature. Whenever the temperature increases, then these covalent bonds will break down. And semiconductors are nothing but the tetravalent atoms. Semiconductors are the tetravalent atoms. Tetravalent atoms means 4 valency electrons will be there. And the best examples of the semiconductors are silicon, germanium, carbon, selenium, like that. And out of all these different, whatever the elements which are present in the fourth group of the periodic table, all those comes under the examples of the semiconductors. And out of the different materials, semiconductor materials, we are using the silicon as a most one, but because it shows it is having the least leakage current and most abundant comparing with the germanium. Okay. And coming to the temperature, so whenever the temperature is increasing, then automatically the forbidden energy band gap or the energy band gap will automatically decreases. Okay, there is a inversely proportionality between both these two. And coming to the bands, as I told that, fine. So just wait a minute, guys. Fine. So coming to the bands, I can take the bands as like this. So it is a valency band and it is a conduction band. Okay. So the gap between both these two, let's take it is the EC and it is the EV. The difference between both these two can be taken as a EG. And while coming to the metals, the EG becomes is equal to 0. That means the valence and covalence band, both these two merge with each other. And while coming to the insulators, we can take it is greater than the 7.2 electron volts, okay, or else 11.1 electron volts. Different textbooks give the different things. And while coming to the EG to the semiconductors, it is approximately equals to 1.21 electron volts, or else you can take 1.12 electron volts. Okay. So if you observe, the EG is 0 for the metals and somewhat more for the semiconductor and still more for the insulator. Okay. So if we keep on increasing the temperatures, then the energy band gap will start decreasing in the case of semiconductors. Okay. And you can take the expression as Eg of T is equal to Eg naught minus beta into T, where beta depends upon the materials. Silicon 1 beta will be there and the germanium 1 beta will be there. Okay, it depends. Okay. So it is a concept regarding the introductions of the semiconductors, bonds and the bands, okay, the dependence of temperature. And next, while coming to the number of electrons in the conduction band can be taken as N is equal to Nc into e power minus of Ec minus Ef divided by Kt, and the number of holes present in the valency band can be taken as Nv into e power minus of Ef minus Ev divided by Kt. Okay, and coming to the mass action law will be there, and that mass action law can be taken as N into P is equal to Ni square. Okay, so these are all the few expressions that you have to know, guys. Okay, and next, coming to the next one, the PN junction diode will be there. So in that PN junction diode, what you have to know is that PN junction diode. So that means whenever the P and N, both these two are combined together, then the depletion layer will forms here. Okay, the depletion layer will forms. And whenever we are doing the forward biasing means connecting the positive terminal of the battery to the P type and negative terminal of the battery to the N type, then the depletion layer width will be very small. Okay, and the conduction will takes place. From P to N direction. Okay, and it is in the milliamperes of range. And whatever the current is happening in this case, that current can be taken as a I is equal to I naught into e power minus V by eta Vt minus 1. Okay, so we can take like this, guys. So here it is the plus I naught into e power V by eta Vt minus 1. And while coming to the V represents the voltage drop across the diode, and eta is the constant that depends upon the silicon and germanium. We can take 1 for germanium and 2 for the silicon. And coming to the Vt is the volt equivalent temperature that can be taken as a T divided by 11,600, or else you can also take Kt divided by Q. At room temperature it becomes is equal to 25 millivolts. Room temperature means this T becomes is equal to 300 kelvins, where K is the Boltzmann constant and Q is the charge of the electron, that is 1.6 into 10 power of minus 19 coulombs. Okay, it is about the diode equation of the PN junction diode. And in this PN junction diode, you have to know about the few more points, that is the equivalent circuit of diode. So the three different types of equivalents will be there. Okay, so the three different types of equivalents means one is the ideal model, and the second one is the simplified model, and next one is the piecewise linear approximation model. So in the ideal model, the diode can be taken as like this: short circuit in the forward bias and open circuit in the reverse bias. So let's take forward and reverse. And while coming to the simplified case, we are going to take like this in the case of the forward bias, and in the case of the reverse bias, the switch is opened here. And while coming to the piecewise linear approximation, so we will take like this, and while coming to the reverse bias, we will take like this. Okay, so here it is the forward resistance and it is the reverse resistance, and it is the cut-in voltage, okay, V gamma. So cut-in voltage is nothing but at which voltage the diode starts conducting is nothing but a cut-in voltage. So these are the different things, different circuit models of the diode. Okay, and after this one, after completion of the PN junction diode concept, of course you have to know some more points here. What are the some more points means? What is the diffusion capacitance? What is the transition capacitance? Okay, so both these two. And what is the what we call conductance of the diode can be given as a I divided by eta Vt. Okay, so what is the resistance of the diode? Okay, so all these things, and along with the expressions also you have to know in this case. Okay, fine. So after completion of this diode concept, the next concept that we are going to hear is regarding the JFET. So coming to the JFET, so how the conduction will takes place here is that, so we are going to take the JFET as like this. We're having the two different types of JFETs will be there. One is the N channel JFET and the second one is the P channel JFET. So coming, if it is a N channel JFET, then generally we are going to take the gate. Okay, if it is the drain and the source, then the drain and source are the N type and the gate is the P type. So we are going to take the structure as like this. So JFET is having the three terminals, gate, drain and source, and it is having only one junction. Okay, and it is completely free from the thermal runaway, and it is less noisy comparing with the BJT. And while coming to the whatever the voltage we are connecting here between the gate and source, it must be the reverse biasing. Okay, that's why the input impedance of the JFET is very high, and the drain and source of the JFET can be interchangeable. Okay, So here if the VGS is 0, then VDS is a non-zero, then the conduction will take place from source to drain. Whenever the VGS is increasing, then the depletion layer width, okay, will start increasing. Why? Because we are doing the reverse biasing here. Then the flowing of electrons from source to drain will be congested, and the drain current will be decreases by keep on increasing the VGS. Okay, so this is one term. And while coming to the drain current, in this case can be taken as a ID is equal to IDSS into 1 minus VGS divided by V suffix P whole square. Here V suffix P is the pinch of voltage and IDSS is nothing but the drain current along the JFET whenever the gate and source, both these two are short circuited. Okay, so it is a drain current expression of the JFET. And apart from this one, you have to know about the what we call amplification factor of the JFET, that is VDS, delta VDS divided by delta VGS. It is amplification factor, and the drain resistance can be taken as a delta VDS divided by delta ID. It is a drain resistance. Yeah, hi Yasim, good evening. Sorry, I am just in flow, I did not look your message. So it is a drain resistance, fine. And while coming to the transconductance, GM can be taken as a output current divided by input voltage. So these are all the different expressions of the JFET you have to remember, guys. So here mu can be taken as a, you can write like this, delta VDS divided by delta ID into delta ID divided by delta VGS. So here if you cancel both delta ID, then again you will direct it to the mu expression. So this one can be written as, I can write this one as a RD into GM. That means in the JFET, the main thing you have to remember that amplification factor must becomes is equal to drain resistance into transconductance. It is the most important formula coming to the JFET. Okay. And so a few more concepts are also there in the JFET. So just like you have to, what are the concepts means, you have to know about the concepts like what we call transfer characteristics and drain characteristics and pinch of voltage, okay, and the formula to the transconductance, that is differentiation of ID with respect to the differentiation of VGS. That means if you are differentiating the ID yeah Fatima, we are having only half an hour, so that's why I'm just trying to cover the entire unit in the half an hour. So I'm just telling in brief. So here ID can be taken as a IDSS into 1 minus VGS divided by VP whole square. Okay, so if you start differentiating this one, then you are going to get the expression as DI 2 IDSS into VP 1 minus VGS divided by VP. Okay, fine. And now here you can take this one as a GM naught into 1 minus VGS divided by VP. Okay, so here GM naught is nothing but is equal to GM, that is the transconductance at VGS is equal to 0. Okay, so GM naught is nothing but GM at VGS is equal to 0. Fine. So it is the case of the transconductance derivation in the coming to the JFET. So after the JFET, then the next thing we have to, the next concept as per our syllabus is that metal to semiconductor junction. Okay, so metal to semiconductor junction, fine. So metal to semiconductor junction means it depends upon the work function. We are having the two different types of metal to semiconductor junction. One is the ohmic junction. Next one is the what we call Schottky junction. Okay, the two different types of junctions are there. So coming to the Schottky junction means here we have to know the work function. So each and every material is having the work function will be there. The work function of the metal is phi m and the work function of the semiconductor is phi sc. So work function means the amount of energy that we have to apply to the material to get the electrons out of the surface. Okay, just like out of the surface means just like the thermionic emission in cathodes. Okay, just like the thermionic emissions in the cathode. Okay. Yeah, Sim, you can watch the recorded videos of the plus classes. So there all these concepts are explained in detail. Fine. So coming to the ohmic and Schottky. Here in the ohmic case, the metal work function must be greater than the semiconductor work function. And while coming to the ohmic contacts, the metal work function must be less than the semiconductor work function. Okay, so in these cases, we are going to get the two different types of junctions we are classifying. And coming to the Schottky junctions, what we can take is that current will flow only in one direction. Okay, current will flow only in one direction. While coming to the ohmic, current will flow in bidirection. Okay, so these are the major classifications, guys. And whenever the metal and semiconductor, both these two are combined to form a junction, then it is called as a heterojunction. Okay, and the best example of the heterojunction is HEMT, nothing but high electron mobility transistor. Okay. Fine. So these are the cases regarding the metal and semiconductor junctions. And while coming to the next one is the low dimensional devices. Low dimensional semiconductor devices. So here you have to know about the 3 points mainly as per given in the syllabus. That is what we call, one is the quantum well, second one is the quantum wire, and the third one is the quantum dot. Okay, the three are there. So what is the quantum well, quantum wire and quantum dot is nothing but, so if you are taking any one thing, that means just like this, okay, and I mean, for example, just wait guys. So if you take any one material like this, then if the electron is moving in the two dimension, if the electron is moving in the two dimension, then it is called as a 2D. Okay, it is considered as a quantum well. And then while coming to the quantum wire, you can take like this, okay, where the electron is flowing only in one direction, it is nothing but 1D. Okay, then we can call this one as a quantum wire. And while coming to the quantum dot, only one simple cubic like of structure will be there, and here the electron is not flowing in any direction, it just acts like a pixel in the quantum televisions, so it is nothing but 0D. So 0D is nothing but a quantum dot. So these are the different low dimensional semiconductor devices, just like the quantum well, wire and the dot. Okay. And after this one, we are having the next concept as LED. So coming to the LED is nothing but a light emitting diode. Okay, so LED is nothing but light emitting diode. So we are using the what we call direct semiconductors for the manufacturing of LEDs. Okay, so while coming to the direct semiconductors means if you're taking the energy band diagram, at the time of de-excitation, the electrons will directly come back to the valency band. So now the de-excitation leads to losing of energy, and in this direct semiconductors, the losing of energy in the form of light or photons. Okay, so direct semiconductors means generally we are taking the help of compound semiconductors. So compound semiconductors means we are taking the third group and the fifth group elements. Okay, third group elements means which are used to get the p-type semiconductors. So the third group elements are indium, gallium, and boron, while coming to the fifth group elements are the arsenic, antimony, and phosphorus. Okay, so if you are taking the gallium arsenide combination, that is third and the fifth type, then you are going to get the red color LED. Okay, so based upon the different combinations, you are going to get the different colors. Fine. And now, so while coming to the whatever the energy of the photon that is coming out. Okay, so let's take that is E is equal to h nu as per the Einstein equation, and it can be taken as a hc by lambda also. Okay, and it while coming to the energy band gaps, so if you're taking the energy band gap, okay, let's take the energy band gap is equal to E. Then what it happens is that energy band gap is nothing but EC minus EV, so you can take directly here EG, and H into C by lambda. Fine. So you can also take this one as a lambda is equal to HC by EG. So after substitution the proper things, then you will get 1.24, okay, divided by EG in electron volts in micrometers. Okay, it is a relation between the lambda and the forbidden energy band gap. Okay, and one more thing, while coming to the light emitting diodes, so here you can take the circuit like this. You can take the circuit like this, voltage and the current will flow, and it is a resistor. And coming to the LED, the amount of light that we are getting out, okay, the intensity of the light depends upon the amount of current injecting into this one. Okay, it is a very most important point. Amount of current that you are getting out is directly proportional to amount of current injecting into this one. If the most amount of current is injecting, then the most amount of light you are going to get. Okay, so it is the one more thing. So, and the next topics are the solar cell will be there. Okay, so coming to the solar cell, it is also just like one type of the PN junction diode, guys. Coming to the solar cell, so we will be having like this one thin N type, and here it is the P type will be there, and coming to the photons are going to be projected here. Then due to the thin layer of the N type, photons will directly enter into the P type and start breaking the covalent bonds. Okay, generally we know that at the N side we are having the positively charged ions will be there. Okay, and at the P side negatively charged ions will be there. Okay, so whenever the photons are coming here, due to the breakage of covalent bonds, the electrons will be liberated here in the P type, and these electrons attracted towards the positively charged ions, that means towards the N side, and now all the electrons will get accumulated here. Now it becomes the negative and it becomes the positive. So by that way, the solar cell is going to provide power to the loads. Okay, they will provide power to the loads. Okay, and in this solar cell you have to know about the fill factors and its efficiency. So fill factor you can understand with respect to the VI characteristics of the solar cell. Right? Okay, so these are all the things, and while coming to the HEMT, high electron mobility transistor will be there. So here the high electron mobility. So first of all, these are used for the high frequency amplification purpose. Okay, high frequency amplification purpose. And why we are getting the high mobility to the electrons? Because due to the two-dimensional electron gas will be there. Okay, two-dimensional electron gas. Okay, we are going to get the high electron mobility in this case. Okay, and the HEMTs are mostly made up of the gallium arsenide materials. The different layers will be there. Okay, So it is the overview of the first unit, guys. Just I want to tell you in a brief, so that's why I went through the little bit fast here to cover all the topics of the first unit in a brief way. Okay, so to get the complete details or to get the complete information along with the class PDFs, okay, along with the doubt clearing sessions, then please take the subscription plan, guys. Okay, so in the subscription plan, that all these details are discussed very clearly, all these concepts, okay, and along with the previous year questions too in the special classes. Fine, so you will get the complete information to crack the JRF. Okay, so here, as I already shown you the different subscription plans here that you may check down. Okay, so and the subscription plans are soon going to hike, okay, are soon going to increase. So before increasing these prices, so if you are anyhow, if you are preparing and if you are planning to take without waiting, you may take the subscription plans. And if you want to take the subscription plan, then use my referral code, that is ASWINIK. Then you will get the 10% discount on any one of the subscription plan. Okay, so I hope all of you are clear, guys. Fine. So it is a present session and we will meet in the tomorrow session 6 o'clock, same timing, with second unit, brief introduction about the second unit. Okay, guys, thank you very much and bye bye.